Bismillahir Rahmanir Rahim. Artificial gravity. Bismillahir Rahmanir Rahim. Artificial gravity and geostationary orbit. Before going to the concept of artificial gravity, we first of all see the basic concept of centripetal force and centrifugal force. We know that the centripetal force is a force which keeps a body to move in a circle. For example, if this toy aeroplane is being circulated by this man with the help of rope, then there will be a centripetal force of the value mv square over r, where m is the mass of the toy, v is the speed of the toy, and r is the radius of the circle. But when the man is pulling this plane towards him in driving or in moving it to move in a circle, then the toy or the object or the mass will be acting or applying a reaction force known as centrifugal force, that is equal in magnitude but opposite in direction as the negative side shown. That is a way of creating the centrifugal force with the help of, by this centrifugal force we create the artificial gravity in artificial satellites. Consider a spacecraft of shape as shown in figure. The outer radius of the spaceship is capital R and it rotates around its own central axis with the angular speed omega. Then its angular acceleration is AC, given by formula v square over r, where v is the speed of rotation, linear speed. This is general formula for getting the centripetal acceleration. It is proved in the previous lecture. And we know that v is equal to r omega. So putting the value of v, then we get the result for the centripetal acceleration in this form. And where omega is the angular speed of this rotating body and equal to 2 pi f, where f is equal to 1 over capital T. So from this mathematical relation of centripetal acceleration, as we see over here, AC is equal to r omega square, and putting the value of omega 2 pi over T in this above equation, we get the following equation: r into 2 pi over T whole square. And by simplifying it to the next step, 4 pi square over T square, and then in the next step we can write it r 4 pi square, and 1 over T is equal to f, so f square, and f square is equal to, can be written as AC over 4 pi square r. So this frequency of rotation of the artificial satellite can be written as 1 over 2 pi under root, by taking square root of both sides, 1 over 2 pi under root AC over r. Over here you can see that if more frequency of rotation, then there will be more centripetal acceleration, as 2 pi is constant and radius of the artificial satellite is also constant. Just by changing the frequency only, centripetal acceleration changes. Or conversely, we can say that when centripetal acceleration changes, frequency of the rotation of the satellite is more. If AC is more, then frequency of rotation is more. So if this satellite is being rotated with more frequency, then it means that there will be more centripetal acceleration, or there will be more centripetal force using this formula. And if v square over r is more, centripetal acceleration is more, then force is more. And all the bodies rotating inside the satellite, all the human bodies or the masses react or give the centrifugal force in the output direction. All the masses of the bodies will react with the centrifugal force, and they tend to move away from the centripetal force or away from the center. All the bodies tend to move towards the wall of the satellite. They tend to move away from the center. In this way, they are stressed, or they are being stressed towards the wall of the satellite using this centrifugal force. And they feel the concept of attraction towards the wall, or they feel a gravity-like effect inside the spaceship, and all the bodies are attached with the walls or boundary of the satellite. If more is the speed of rotation or frequency of rotation of the satellite, then gravity acceleration due to gravity, as centripetal acceleration is more, then centripetal force is more. In reaction, centrifugal force will be more, and this acceleration due to gravity, this centripetal acceleration will behave as acceleration due to gravity. And so we can write this formula to this form, and which shows that if you want the acceleration equal to the acceleration due to gravity, then you will have to move the satellite with this frequency. If you are known with the radius and 2 and pi are constant, so by putting the value of g is equal to 9.8, you can get the frequency of rotation. If the satellite is being rotated with that specific frequency, the human bodies or the masses inside the satellite will feel the gravity effect equal to the gravity of the Earth. Okay. Now, the next topic. Geostationary satellites or geostationary orbit. Satellites which are moving around the Earth in such a way that they look stationary to the body who is facing that satellite at the Earth. And the human being which look that satellite and feel it that it is stationary, then this type of satellite is known as geostationary satellite. How? If you observe that both the geostationary satellite, or both the artificial satellite and the Earth are rotating, and if the speed of artificial satellite becomes speed of rotation of artificial satellite becomes so much, if the speed of artificial satellite is in such a way that the point which is located on the Earth is in front of the satellite always remain in front, or the speed of, if the speed of rotation of the Earth and the speed of rotation of the satellite becomes in such a way that the time period for the both becomes equal. If the Earth rotates complete circle, complete rotation or spin in 24 hours, and the satellite also moves a complete round trip in 24 hours, then it means that this point which is in front of the satellite, facing the satellite on the Earth, it will always remain in front of the satellite. If the Earth moves a little forward, then the satellite will move accordingly, but the point will remain in front. If the satellite comes over here, the point will come over here, and then again will The point comes over here, the satellite will come over here, and all the points, all the time the point will remain in front of the satellite, and the point or the body in front of the satellite will feel that the satellite is not moving with respect to him. This type of satellite is known as geostationary satellite. And the orbit in which this satellite is rotating, this type of orbit is known as geostationary orbit. Now we find the radius of this geostationary orbit. To find the radius of this geostationary orbit, first of all, we have to calculate the orbital speed of the artificial satellite. This satellite is moving in a circular motion, so it has a centripetal force of value mv square over r, and this centripetal force is being provided by the force of gravity. And we know that the gravitational force can be calculated by using the general formula G m1 m2 over r square, where m1 is the mass of the satellite, m2 is the mass of Earth, and r is the radius, or the distance from the center of Earth to the satellite. This force of gravity provides a centripetal force to this satellite. By equating these two terms, we get velocity square is equal to under root of gme over r, according to this formula. From here, we can take the advantage of calculating the time. We know that total time of the complete round trip can be found by the velocity or the speed formula, that s is equal to v over t and t is equal to s over v, where s is the distance and v is the speed. So how much distance satellite covers? 2 pi r, complete circle, and speed is given by this formula. It means the speed formula is 2 pi r over t, and from here we can calculate the capital T, a time period. Okay, by comparing these two terms, 2 pi r over t, and we can find the radius. You know that the time period of both the satellite and the Earth is 24 hours. So putting the value of t equal to 24 hour over here, capital G, gravitational constant 6.67 10 per minus 11 Newton meter square per kilogram square, and mass of Earth 6 into 10 to the 24, 6.4 into 10 to the 24, and 4 into pi is equal to 3.14. So putting the values of all the parameters, we get the value of radius at which body will rotate with a time period of 24 hours. By changing the radius, the time will be more. So if the time period of satellite and Earth becomes different or more, time period for the satellite to rotate around the Earth becomes more, then the time period will become different, and the satellite will not be looking a stationary satellite to the bodies on the Earth. Time period must match. So for matching the time period, a satellite have to be revolved in a fixed circle of fixed radius. And that radius should be 4.23 into 10 to the power 4 kilometers. It is very necessary. Otherwise, the body or the satellite moving in circle orbit will not be looking stationary. So artificial satellites orbit around the Earth. They are put into the orbit by the rockets. Low flying satellites have the acceleration equal to g. In circle, it has an acceleration that is given by the formula A is equal to v square over r as centripetal acceleration. And from here we can find that A is equal to g and g is equal to v square over r. So V is equal to RG. So we can find the speed of satellite by using this formula, which are rotating near the Earth, and that is 7.9 kilometer per second. If a body is rotating with so much high speed near the Earth, or a body is thrown with so much high speed near the Earth, then the body will rotate and it will not fall down on the Earth. And this type of satellite is known as artificial satellite near the surface of Earth. But the satellite has to move with so much velocity. This is very fast velocity. Next, this is the minimum velocity necessary to put the satellite into the orbit, that is 7.9 kilometers. So the time period required for this satellite, time period of this satellite to cover the whole circle, whole orbit, will be equal to total distance divided by total speed. Total distance is 2 pi r and speed is 7.9 kilometer per second. So almost 84 minutes will be required if the body is moving with so much high speed, or the satellite is moving with this speed. Then it will use 84 minutes to cover a complete round trip. If the satellite is at a height h, g decreases. As the g decreases, speed decreases. And speed decreases, then it means that speed decreases, then time increases. So for higher orbits, the time period will be more. Orbital speed of the Hubble Space Telescope. Determine the speed of the Hubble Space Telescope orbiting at the height of 384 kilometers above the Earth's surface. And that speed can be calculated using the same formula as we have derived over here, GME over RE, where R is the distance. So speed will be 1.01 kilometer per second. It's also big speed, large speed, and the time required will be 27.5 days. If the satellite is to remain in an orbit of radius r, the speed must have precisely this value. The closer the satellite to the Earth, the smaller is the value of r and greater is the orbital speed that must be. And the mass m of the satellite does not appear for a given orbit. A satellite with a large mass has exactly the same orbital speed as a satellite with a small mass. So these are the points to remember, important points in the discussion of satellite motion. Thank you for watching the video lecture. Please visit the website www.cancollege.com and subscribe this channel for more informative lectures and videos on all subjects. Thank you.